Hi, calculus student. This video is for chapter 410, Antiderivatives. So it's the last chapter of chapter 4. We are preparing for chapter 5, which is integral calculus. So this is the beginning of integral calculus. And what happened is we kind of wrapped the whole thing about derivative by thinking about what if I don't want to do derivative? I have an answer and I want to find the original function. So that's the notion of antiderivative. Antiderivative of a function can be viewed as reversing differentiation. So you have a function, you did differentiation, you get an answer. You want to look back as to where it comes from, so that the original function is called big F of x, capital F of x, such that f prime of it is actually your function that you have for all x in the domain of f. So because the derivative of a constant is 0, so if f is an antiderivative of big F is an antiderivative of the function f, then anytime you do a derivative of f, big F of x plus c is as also an antiderivative of f. Meaning, if you want to find what is that you have come from, so that when you do a derivative of the big F of x, it become F of x. You could have any constant. So an example would be if I have a function, big F of function equal to x squared, and so my F of x is 2x because this is the derivative of the original function. So we call this the differentiation. So this going back is the antiderivative. Okay, but you can also notice that f of x, if I have x squared plus 1, when I do derivative, I do have 2x also. So I can really figure out if my original function is x squared or x squared plus 1, or actually x squared plus any constant c. So whenever you have a antiderivative big F of x, any c add to it is also an antiderivative of f. So that is the special thing about antiderivative. So we would say if you are to find antiderivative, you assume that you are finding the general form of the antiderivative is a family of functions. So it's not just one function of big F of x. It's big F of x plus c. So you always write plus c. Please always write plus c to make sure that you cover all different functions. So how do I do it? The way to do it is really to look back. Where would this come from? Where would big F of x come from, so that when I do a derivative, it would become this F of x. So I want to find all the antiderivative, the general form of x cubed. So what original function would it be, so that when I do the derivative, it become what would it be? So that when I do the derivative of it, I would have f of x equal to x cubed. Right? So when I do the derivative, this is a derivative, d dx. When you do d dx, you have x cubed. So you know that because of power rule, anytime you do a derivative, the power is lower. So it must be some form of x to the fourth, right? So is it x to the fourth? No, because when you do x to the fourth, the derivative is what? Derivative is actually 4x cubed, right? So if I want my original function to be x cubed only, so this must be 1/4 of it. So I must have 1/4. In the beginning, I have 1/4, so that when I do the derivative, I should actually say here, I should actually say thinking outside, if I have x to the fourth, my derivative is 4x cubed. So in order for me to do x cubed, it must be 1/4 of the original one, right? So this is, that's how you think about it. So the antiderivative is 1/4 of x to the fourth plus c. Okay, so you have to do some thinking. Later on, we have a power rule that helps you to do this, so don't worry. What about if my answer of a derivative function was 1 over x, what is the original function? So you can actually write it this way. Okay, what is the big F of x? Big F of x, before you do antiderivative, so you refer to the differentiation formula. So your answer was, so you look at this side, the answer was 1 over x. So where does it come from? Oh, it comes from ln x. Now notice this formula that we have here is not the ln x that we used to have. What happened is 1 over x is a function that has the domain of x not equal to 0. So it includes both positive and negative x. But if you just do ln x, that would only include the positive side of x. So the way to cover the whole of 1 over x is for the original function to be ln absolute x. ln absolute x. This formula is from the book, and I have filed it on Canvas, so you can look at it. So for b, f of x equal to 1 over x, the original function before you do the derivative was ln absolute x plus c, according to the formula. So you can, if you have the formula, you can tell where they are. What is the original function? So to check that you get it right, so you can say check. If I do the derivative of f prime, big F prime of x, do I get a 1 over x? So that would be 1 over absolute x. And for x being, so, and that would include a 1 over x, but x is not 0. Okay, so cosine x. What is the original function so that when I do the derivative is cosine x? Everybody knows is sine x, so sine x plus c. Okay. Do I do negative? No, because when you do the derivative of sine x, you only get cosine x. Okay. What about e of x? What was the original function? So when you do a derivative, you get e of x. So you can say here, check. When you're doing antiderivative in the beginning, you get a little confused. So what you can do is, if I do sine dd sine x, do I get the original function back? It is cosine x, so it is okay. Okay. So and that is 1 over x if x is ln. It's kind of strange. So what is the original function so that when I do the derivative is e of x? Of course it's e of x, but plus c. Okay, so it's very easy. You just have to be very, it's kind of like a division. If someone asks you 63 is 9 times what, like that. Okay, it's the opposite of something that you have known. A new notation for calling antiderivative. You see how clumsy it is when we will be just talking about, can you give me the antiderivative of e of x? So what would, it would be nicer if we have an operator that can actually do the operation of an antiderivative, which is the opposite of d dx. So you can think of d dx as an operation that operate on big F of x, right? And you will get your original function f of x, and we call this operation d dx, right? F prime, you get this. But now you go back, we want to have an operator, and this operator is the integral operator, the integral dx. Now they also have the dx there, so if I'm going this way, it is kind of like dividing. I'm going back, we're multiplying. So this just tells you that this is the integral constant. Kind of like when you're doing derivative, you can tell this is the constant where, not the constant, the variable that you are doing derivative with. So you have dx and then an integral long as sign like this, and it's called the indefinite integral. So this symbol is called indefinite integral. And you write it as indefinite integral of f of x is equal to f of x plus c. Okay, because this is a plus c. Like that. Going derivative is d dx. Going back is integral. And is you will provide the antiderivative of f of x. So earlier when we do the example of x cubed, it's quite clumsy to figure out what the original function is, we would have to think of, if it is x to the fourth, then it is too much, and then you have to divide, right? So you finally have a general power rule for integral. So the general power rule is, if you do integral x to the n dx, is x to the n plus 1 over n plus c. So you can see that in this particular case that we have earlier, if the final function is x to the cube, the original one was x to the fourth over 4. X to the fourth. So these two matches. So it's x to the n plus 1 over n if the original start with n. But this only works if s n is not negative 1. So not for 1 over x. Not y, because this is just ln x. And ln absolute x plus c. Okay, so the other integral rules would be, you can refer to the formula sheets. So this is the one that is like a general power rule. So let's do a few. Evaluate each of the indefinite integral. So just like limits, you can, or different derivative, you can separate them into individual ones. So we do that too. So if it's a constant multiple, it's just a constant multiple. So it would become 5x squared dx minus 7 x cubed dx plus 3 x dx plus 4. Well, 4 is, kind of constant. So 4 integral dx. So now these x to the n can be done by the power rule. So be 5x 2 plus 1 over 2 plus 1, right? Minus 7 x to the fourth over 4. Plus 3 plus 1 is 4, right? 3, it is 1, so x2 over 2. Plus what about 1? That is just x. Because remember, when you do derivative, 4x derivative is just 4, right? And plus c. So this would be, rewrite it back, would be 5 over 3 x to the cube, x cubed, minus 7 over 4 x to the fourth. There's a lot of fraction. Plus 3 over 2x squared plus 4x plus c. And what we're saying is, this is the original function that was not undergoing and has not been undergoing differentiation. If I do a derivative of it, I will have 5x squared, blah, 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 like that. And remember, plus c. So we have a few more. So maybe I'll just do one more, and then because this can be done by power rule. So this is an integral of a lot of power of x. So, but there is a divide x. It is not a quotient rule. Okay, no quotient rule for integral. Integral is just lookup or power rule. So what you do is you just simplify them as x squared over x being x. And then square root x over x is x to the 1/2 over x1 is 1 over square root x, or x to the negative 1/2. Maybe I should write x to the negative 1/2, right? 1/2 minus 1 is x to the negative 1/2 plus 4 x to the 1/3, right? dx. And I'm going to use power rule one by one. So be x dx. Remember, no quotient rule, no power rule, only power rule. The power rule is add and divide. dx plus 4 x 1/3 dx. So don't be confused about doing derivative or antiderivative. So this is x to the 1, so it's 1.1, 2 over 2 plus negative 1, negative 1/2 plus 1 is 1/2 over 1/2 plus 4 times x to the 1/3 plus 1 will be 4 over 3, right? Over 4 over 3. Simplify out plus c. Simplify. So it'll be x squared over 2 plus 2 square root x plus 3, because this 4 and 4 cancel, this 3 goes up. 3x to the 4 over 3 plus c.